Hello, welcome to today's lecture. We're going to start chapter 10. We're going to talk about sequences and series. 10.1 Overview on sequences. We are on page 1 of the notes. So in general, what is a sequence? What is a sequence? Officially, we say that a sequence is a function. A sequence is a function. So function notation, f of a variable. F of variable n, which we usually denote by a sub n. So a sub n. Instead of using x, we're using a variable like n. There is a reason for that. A sequence is a function f of n equals to a sub n, such that the domain of the sequence is natural numbers, is n, which is natural numbers or counting numbers, and the range of the sequence is R or real numbers. And the range is R or real numbers. So this function takes elements in n natural numbers and map them to R as real numbers. So it takes each variable like n and map them to f of n, which we also denote by a sub n, and we call it the general term of the sequence. Note that. Note that. We can list the terms of a sequence as a sub 1, comma, a sub 2, comma, a sub 3, comma, a sub 4, comma, a sub n, comma, the rest of the terms. We say that a sub 1 is the first term of your sequence. This is your first term. A sub 2 is the second term. A sub 3 is the third term. A sub 4 is the fourth term, and a sub n is the general term of your sequence. Perfect. Very well. We are still on page 1. Let's go over some examples to feel comfortable about this definition. For example, Suppose you have a sub n. This is your sequence 1 over 2 raised to n. First of all, here you have a function. A sub n equals to 1 over 2 to the n is a function. So what's the meaning of that? It means that for sure you can graph this function. And for sure you can find the limit of this function while n goes to infinity. So let's graph the function first. What's the graph like? What's the limit at infinity like? There you go. Let us plug in values for n and graph our function n 1 over 2 to the n. Note that the domain of your function, the domain is n. It means that the starting value, the starting number is going to be 1. So if you plug in 1 for n, you get 1 divided by 2 to the first power or a half. So the first point on the graph of the function is 1 and a half. There you go. Let's graph this guy. And f of n. So on horizontal axis, instead of having x, we have n. On the vertical axis, we have f of n, the y values. 1 and a half. So this is 1, this is 1, 2, 3, 4, 5, and you can continue. One and a half. This is your first term of this sequence. Let's plug in 2. If you plug in 2, you get 1 over 2 squared, which is 1 over 4. Second term of this sequence is 1 over 4. So second point is 2 and a 4. A sub 2. Okay. Seems like this graph is a decreasing graph. Let us plug in 3. 1 over 2 to the third is 1 over 8. As you can see, these y values are getting smaller and smaller. So 3 and 1 over 8, a sum 3. Let's plug in another value, like 4. 1 over 2 to the 4th is 1 over 16. It seems like our guess is correct. The graph is decreasing. A sub 4. First of all, note that we cannot connect these points. Do not connect these points. It's actually a discontinuous or discrete graph. Discontinuous or discrete graph. It means that there are gaps in between. There you go. As n goes to infinity, the graph of the function approaches horizontal axis, so the y value is going to be 0. Take a look at this. The limit of 1 over 2 to the n, while n goes to infinity, is, look at the graph of the function, is equal to 0. So I expect you to ask, what's the connection between limit of 1 over 2 to the n and the limit of this function that you learned in Calc 1? How do you calculate the limit of 1 over 2 to the x while x approaches infinity? In this case, remember that on the denominator, you have 2 to infinity. You get 1 over infinity, 1 over infinity, which is 0. So, in general, to understand the limit of a sequence as a function, you can always work with limit of a continuous function. Instead of using n, you can use x. Whatever the limit is, that's going to be the limit of your sequence. Another example for you. Consider this sequence. A sub n is defined as, okay, -1 to the n over n squared plus 1. Again, you have a function. A sub n as a sequence is a function. It's a discontinuous function. We can graph it, and at the same time, we can find the limit at infinity. Okay, let's graph this function by plugging different values in a sub n. If n is equal to 1, you get -1 raised to 1 times 1 divided by 1 plus 1, we get -1 over 2. Negative. Let's take a look at the graph. And f of 1 and minus a half. 1, 2, 3, 4. -1 and 1. Very first point is going to be 1 and negative a half. 1 and minus a half. A sub 1. Okay, let's plug in more values. Suppose n is equal to 2. We get -1 squared times 2 divided by 4 plus 1, which is 2 over 5. Very well. When n is even, you get a positive number. 2 over 5. And it's 2. 2 over 5 is going to be roughly here. A sub 2. Let us plug in 3. If I plug in 3, I get -1 to the third times 3 divided by 9 plus 1, which is -3 over 10. Very well. My third term is a negative number, negative fraction. A sub 3. Let us plug in 4. -1 to the 4th times 4 divided by 16 plus 1, which is 4 over 17. My fractions are getting smaller and smaller, and they're getting closer and closer to the horizontal line. So it seems like if I plug in more values, and if I continue this process, all terms are getting closer and closer to horizontal axis. So here, if you have 5, with a negative number, 6, 7, 8. You can continue this process. You can plug in different values. You get a sub 5, you get a sub 6, a sub 7, it's very close, place of 7, a place of 8. As you can see, these points, even though they are some of them positive and negative, eventually they're getting closer and closer to 0. So you can say that, hey, the limit of -1 to the n times n divided by n squared plus 1 while n goes to infinity is equal to 0. That makes sense. These values are getting closer to horizontal axis, and horizontal axis, your y value is 0. So the limit at infinity is equal to 0. Again, we can get back to cat 1 and find the limit of this function. Limit of -1 to the x times x divided by x squared plus 1 while x goes to infinity. Since the degree of the denominator is greater than the degree of the numerator, this guy is going to be simplified into -1 to the x divided by x while x goes to infinity. Number divided by infinity is equal to 0. We are on page 2. Let's talk about more limits. Example. Find the limit of the following sequences, of the following functions. So the first one is -1 to the n divided by n squared plus 1. The second one is cosine, the arbitrary function, n times pi. Our goal is to analyze these two functions. Very well. You can say that, well, for the first one, if we use my f of x, it's going to be -1 to the x divided by x squared plus 1 while x goes to infinity. On the numerator, it doesn't matter if you have an even number or odd number, you eventually get either +1 or -1. So your numerator is just a constant, it's just a number. Your denominator goes to infinity, so you have a constant over infinity, which is equal to 0. So the limit while n goes to infinity is equal to 0. What about cosine n times pi? Let's think about this trig function for a moment. If n is equal to 1, cosine 1 times pi is cosine of pi, which is equal to negative. If n is equal to 2, you get cosine of 2 pi, which is equal to positive. If n is equal to 3, I get cosine of 3 pi. Okay, I know that this guy is -1. If n is equal to 4, I have cosine of 4 pi, which is +1. Okay, it seems like I'm just going in between -1 and 1, jumping from -1 to 1, from 1 to -1, -1 to 1. It doesn't give me a constant value. The limit doesn't exist and we say that we have a divergent sequence. We can continue this process. Since the limit of cosine n pi doesn't exist. We don't know if it's -1 or 1. We cannot decide on that. Does not exist. We say that this sequence cosine n pi is divergent. So what about this limit? The limit goes to 0. In this case, we can say that, hey, this sequence is a convergent sequence and it converges to 0. Sequence -1 to the n over n squared plus 1 converges to 0. Well, another example for you. Do we have a convergent or divergent sequence? So here you have a sub n, which is equal to 4 n cubed divided by n cubed plus 1. So what's the limit while n goes to infinity? Let us get back to calc 1. We know that the limit of 4x to the third divided by x to the third plus 1 while x goes to infinity. Note that the degree of the numerator and the degree of the denominator, they are the same. Both of them are free, so you can ignore the lower terms. You get 4x cubed divided by x cubed. You can cancel out these two. Is equal to 4. The limit exists, and the limit is equal to 4. So you can say that, hey, the limit of this sequence, limit of 4n cubed divided by n cubed plus 1, while n goes to infinity, is equal to 4. The limit exists, and we say that the sequence converges to 4. Eventually, all y values, all terms of this sequence, while n is very large, are 4. Okay, so now that we talked about sequences, before going into more properties of sequences, we're going to talk about series. So how do we use sequences and how do we define a series? There you go, sequences. With terms a sub 1, a sub 2, a sub 3, a sub 4, a sub n, and the rest of it. We can create something new by adding these terms. So, by adding the terms of a sequence, instead of listing them this way, we're going to take these and add them all together. We can create something new, and we call it a series. Okay, so a sub 1 plus a sub 2 plus a sub 3 plus a sub 4, and So when you're adding the terms, we can use symbol sigma, ugly sum, ugly s, sigma. The sum of these terms, you can write it in compact form and say that, okay, we are summing the terms of A sub k. K ranges between 1 to infinity. This is called a series. By adding the terms of your sequence, you create something new and you call it, hey, I have a new function and I call it a series. Okay, now that you formed your series, something interesting about series is the partial sum of elements of that series. So partial sums, which is denoted by a sequence S sub n, is defined this way. S sub 1 is the first term of your sequence and your series, A sub 1. S sub 2, the second partial sum, is A sub 1 plus A sub 2. S sub 3 is A sub 1 plus A sub 2 plus A sub 3, and you can continue this process. And for example, you can define S sub n, which is A sub 1, A sub 2, A sub n, which is the sum, A sub k, k starts from 1 and stops at n. So what did we do so far? We took a sequence, A sub n, we added the terms of this sequence, and we defined a series. Then we took partial sums of this series, S sub n, and we defined them this way. S sub 1 is A sub 1, S sub 2, A sub 1, plus A sub 2, S sub 3, A sub 1, A sub 2, A sub 3, and S sub n, which is A sub 1 plus A sub 2 plus A sub n, which is all of these are series themselves. A sub k, k starts from 1 to n, and we call it the partial sums. So if you take each of these and form a sequence, if this sequence is convergent, you say that your series is a convergent series. So note, if the sequence S sub n of partial sums is convergent, then we say that the series A sub k, k1 to infinity, is convergent. So in this case, you say that infinite series a sub k, k starts from 1 to infinity, is actually the limit of a sub k, k starts from 1 to n, while n goes to infinity, and this is equal to the limit of S sub n, sequence of partial sums, while n goes to infinity, and if that limit exists, and that limit is equal to L, it's exactly the limit of your infinite series. Otherwise, you say that the series is a divergent series. Okay, let's go over some examples to see what's going on. We are on page 4 now. Page 4. Okay, in this example, one series is given to you. You have series of 1 over k times k plus 1. K starts from 1 and it goes to infinity. There you go. Okay. Question says, is the series convergent? We're going to go over techniques and tricks how to analyze series later. For now, just take a look at some of the terms of this series. So let k be equals to 1. So when k is equal to 1, the first term is 1 over 1 times 2, which is a half. When k is equal to 2, you get 1 divided by 2 times 2 plus 1, which is 1 over 6. Okay, this is a sub 1, this is a sub 2, so a sub 1, a sub 2. If k is equal to 3, we get 1 over 3 times 3 plus 1, which is 1 over 12, a sub 3, and you can continue this process. To form this series, we need to add these terms together and to form the partial sums Sn. We need to form S1, which is A1, a half. S2, which is A1 plus A2, a half, plus 1 over 6. This guy is equal to 3 over 6 plus 1 over 6, 4 over 6. S sub 3 is A sub 1, A sub 2 plus A sub 3. You already know that A sub 1 plus A sub 2 is 4 over 6. A sub 3 is 1 over 12. So you get 8 over 12 plus 1 over 12, 9 over 12. S sub 1, the first term of the sequence of partial sums is a half. The second term is 2/3. The third term is 3 over 4, and so on. If k is equal to 4, let me write this out for you as well. 1 over 4, 4 plus 1, which is 1 over 20. A sub. So we can form S sub 4, which is S sub 3 plus A sub 4. This is 9 over 12 plus 1 over 20. Or here, if you simplify this by, you get 3 over 4, which is 15 over 20, 16 over 20. continue finding the rest of these terms and add them to 16 over 20 and so on, the limit of the partial sum Sn while n goes to infinity is going to be equal to, again, later on, we're going to use techniques to write this fraction into the difference of two other fractions, and we're going to discuss the techniques to actually find the limit directly using the formula. Okay, let's start 10.2. Discuss the series, the sequences, then we're going to discuss the series. To have more terminologies, more definitions related to sequences, so let's discuss them. (10.2) theorem. So here, suppose let f be a function, and we define this function this way. We say that f of n is equal to a sub n for positive integers n. If the limit of f of x while x goes to infinity is equal to L, then the limit of a sub n while n goes to infinity is equal to L as well. Note that if L is a constant, if L is a unique constant, then we say that the sequence AN is convergent. Otherwise, we say that sequence A sub n is divergent. Okay, examples. Still in page 1. Example. Find the limit of the following sequences. The first one is a sub n equals to 3n cubed divided by n cubed plus 1. Okay. We already saw that the limit of 3x cubed over x cubed plus 1 while x goes to infinity is equal to 3. So you say that the limit of a sub n while n goes to infinity is equal to 3. since this is a unique constant, we say that an converges to 3. Okay, let's review a little bit. In general, if you have infinity over infinity or 0 over 0, you can use L'Hopital's rule, which says that the limit of f over g while x goes to a, x goes to infinity, whatever it is equivalent to the limit of f prime over g prime while x goes to . So, take a look at this function. Here you have limit of 3x cubed over x cubed plus 1. X goes to infinity. This is infinity over infinity. So we can apply L'Hopital's rule and take the derivative of the numerator, take the derivative of the denominator. You get 9x squared divided by 3x squared, and x goes to infinity. You can cancel out x squared and x squared. 9 divided by 3 is equal to . Another example, please. B. They have this series Bn is n plus 5 over n raised to n. Okay, there you go. Again, we're going to find the limit of the function, which is equivalent to this sequence, limit of function x plus 5 over x raised to x, x goes to infinity. First of all, let us simplify this expression here and write it as the limit of x divided by x, 1 plus 5 divided by x raised to x while x goes to infinity. Okay, how do we find this limit? If you plug in infinity, you get 1 plus 5 over infinity raised to infinity, which is 1 plus 0 raised to infinity, 1 to infinity, which is in indeterminate form. So y is equal to 1 plus 5 over x raised to the x. We can take ln of both sides. I'm getting back to calc 1. You can take ln of both sides and say that, hey, ln of y is equal to ln of 1 plus 5 over x raised to the x. Based on the properties of ln, I can take this exponent and write it in front of ln. So I have ln of y equals to x times ln of 1 plus 5 over x. Now, if I take the limit, it's going to be infinity times ln of 1, which is 0. So it is infinity times 0. What can I do? I can write x on the denominator this way. This is ln of y equals to ln of 1 plus 5 over x divided by 1 over x. Then I can apply L'Hopital's rule. So the limit of ln of y while x goes to infinity is the limit of ln 1 plus 5 over x while x goes to infinity is going to be ln of 1 divided by 1 over infinity, which is 0. So you get 0 over 0. Now you can apply L'Hopital's rule. So here you have the derivative of your ln, which is negative 5 over x squared divided by 1 plus 5 over x. The whole thing is divided by negative 1 over x squared. Very well. I can cancel out x squared plus I get 5 divided by 1 plus 5 over x. If you take this limit while x goes to infinity, this is 5 over infinity, which is 0. This is equal to 5. So ln of y is equal to 5. Y is e to the 5th power. So the limit of your function is e to the 5th. So the limit of your sequence while n goes to infinity is e to the 5th power. And since this is a unique number, we say that the sequence converges to e to the 5th. So the sequence converges to e to the 5th power. Another example for you. The last sequence, Cn, is n raised to 1 over n. There we go. We can look at our function. Limit of x raised to 1 over x while x goes to infinity. So this is infinity raised to 1 over infinity, infinity raised to 0. Okay. So let's see. Let y be x raised to 1 over x. Then we can take ln of both sides. Ln of y is equal to ln of x raised to 1 over x. Since you have ln, you can take the exponent and write it in front of ln. So you get ln of y equals to 1 over x times ln of x, which can be written as ln of x over x. Now, if you take the limit of ln of x over x, while x goes to infinity is infinity over infinity. Now you can apply L'Hopital's rule on the right hand side. So ln of y is equal to the derivative of ln of x divided by the derivative of x, which is 1 over x divided by 1 over x. So ln of y is equal to 1 over x. The limit ln of y is equal to the limit of 1 over infinity, which is 0. So y is equal to e to the 0, or y is equal to 1. It means that the limit of your sequence, the limit of n raised to 1 over n, while n goes to infinity, is equal to 1. And since 1 is a unique constant value, you say that the sequence converges to 1. Definition. So we are on page 2 of the notes. Definition. So suppose you have a sequence with A sub n be a sequence. First of all, we say that this sequence is increasing if n is less than n plus 1, then you can conclude that the general term of an is less than the general term of A sub n plus 1. We say that a sequence like A sub n is decreasing if n is less than n plus 1 on x-axis, your y values are getting smaller and smaller. So an is greater than an plus 1. In general, you say that A sub n is monotonic if it is increasing or decreasing. We say that a sequence like A sub n is bounded above if there is a constant like m, a number like m, such that A sub n is less than equals to m for all n, and we say that sequence A sub n is bounded below if there is a constant like m such that an is greater than equals to m for all relevant. What do I mean by that? Let us graph this and take a look at the graph. For example, for bounded above, this is n, this is f of n, you have some terms. So suppose you have this sequence, it starts increasing and then it continues the behavior like this. So of course you can find a horizontal line, constant function n, such that all terms for all relevant n, all of those are less than m. All of these y values are less than m. So we say that the sequence is bounded above by m. You can say that your sequence is bounded below by another constant if it behaves like this. Suppose it starts going this way, and then it continues the behavior like this. All of the terms are bounded below by this constant function m. All of the terms are greater than this constant m, and we say that it is bounded below. So bounded above and bounded below. And in general, we say that a sequence is bounded if it's bounded above and bounded below. Okay, we're still on page 2 of 10.2. Example. Question says, analyze the behavior of this sequence. You have a sub n, which is equal to n to 3 halves divided by n to 3 halves plus 1. First of all, since we want to analyze the behavior of this sequence, let us take the limit while n goes to infinity. Infinity and a sub n for general terms at infinity are important for us. We can just skip the first, for example, 10 terms, the first 20 terms. Those initial terms are not very important. The most important part about a sequence is the end behavior of the sequence. So the limit of a n while n goes to infinity is equivalent of finding the limit of x raised to 3 halves divided by x raised to 3 halves plus 1 while x goes to infinity. So by applying L'Hopital's rule, this guy is equal to 1, and you can say that the limit of the function is equal to 1. Another example. Now suppose you have Vn, which is, okay, it has -1 raised to n into 3 halves divided by n to 3 halves plus 1. Well, the only difference between these two sequences is -1 raised to n. Okay. The limit of Vn while n goes to infinity, equivalently, you can find the limit of -1 to the x raised to 3 halves divided by x to 3 halves plus 1 while x goes to infinity. When x goes to infinity, if you forget about -1 to the x, you can apply L'Hopital's rule and you can get 1 here. But if x is even, you get 1. If x is odd, you get -1. So we say that the limit does not exist, and this sequence is a divergent sequence. So here you have an to be convergent, and here you have Dn to be divergent sequence. Okay, let's see what's left. Geometric sequence. We are on page 3. geometry sequence is defined this way. R to the n, R is the ratio, n is just the exponent. The limit of R to the n while n goes to infinity has different cases dependent on your ratio. If the ratio, if R is between -1 and 1, if you have a fraction between -1 and 1, then it is 0. If R, the ratio is exactly 1, then it is equal to 1. If R is greater than 1, or if R is less than -1, you say that this guy does not exist. Okay, example. So this example says find the limit of the following sequence. The first sequence is a sub n equals to 5 times 0.6 to the n minus 1 over 3 to the n. So the limit of a sub n while n goes to infinity is equal to the limit of 5 times 0.06 to the n while n goes to infinity minus the limit of 1 over 3 to the n while n goes to infinity. Note that here you have 0.6 raised to n, which is 6 over 10 raised to n, and as you can see, we have a geometric sequence. Since R is 6 divided by 10 is a number between -1 and 1, so the limit is just 0. What about this one? You have 1 over 3 to the n, which can be written as a third to the n. Your ratio, your R, is a third. A third is a number between -1 and 1, and the limit goes to 0. So both of these are 0. Their subtraction is 0. So the limit of a sub n while n goes to infinity is 0. Another example for you. Find the limit of here you have Pn, which is defined as 2n squared plus n divided by 2 to the n times 3n squared minus 4. Okay. Perfect. So let us write this in a simpler format so we can analyze this sequence. This guy can be written as n 2n plus 1 divided by 2 to the n 3n squared minus 4. Or you can write this guy this way. You can write it as 1 over 2 to the n. Let's separate this. 2n squared plus n divided by 3n squared minus 4. So we can take the limit of the first function and multiply by the limit of the second function. So limit of bn while n goes to infinity is the limit of 1 over 2 to the n while n goes to infinity times the limit of 2n squared plus n divided by 3n squared minus 4 while n goes to infinity. The first limit is equal to 0. Why is that? Because you have 1 divided by 2 to n, which can be written as the limit of a half to the n, which is a geometric sequence, and or the ratio is between -1 and 1, so the limit is 0. This limit is equal to 0 times anything equals to 0. And as you can see, the limit of the second function is 2 over 3. 0 times 2 over 3 is 0. Very well. In Calc 1, you learned about squeeze theorem. So let us review the squeeze theorem one more time. Review of Calc 1. Squeeze theorem or sandwich theorem. If you have 3 functions, function f, function h, and function g. Function f is less than function g is less than function h. If the limit of f of x equals to limit of h of x, so the lower function, the upper function, they have limits, and those limits are equal to each other. Then you can conclude that the limit of gx is also equal to the limit of f of x and h of x. So let's call it L. It must be. So we're going to use squeeze theorem or sandwich theorem in sequences. Since sequences are just functions, we can apply this theorem. Let's take a look at this example. Example says, find the limit of sequence Bn, which is cosine n, divided by n squared plus 1. So since we have cosine n, cosine function is always between -1 and 1. It's always true. If you graph your cosine function is oscillating between 1 and negative. It's always bounded between -1 and 1. Cosine as y value is bounded between -1 and 1. Now, since n squared plus 1 is always positive, divide all sides by n squared plus 1. Divide by n squared plus 1. N squared plus 1, n squared plus 1, n squared plus 1. So in the middle, you created your Bn. Bn as a sequence is bounded between 2 other sequences, -1 over n squared plus 1 and 1 over n squared plus 1. Take the limit of all of these. Limit, 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 while n goes to infinity. that limit of -1 over infinity is 0. You don't know the limit of Bn, so you copy this down, and you know that the limit of 1 over infinity is 0. Using sandwich or squeeze theorem, the limit of Bn must be 0. So your sequence is convergent to 0.